Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is square root of LCA convolution. The problem appeared in December long challenge and has a difficulty level of medium. The prerequisites for this problem are trees, quadratic residue, and the Tonelli-Shanks algorithm. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the detailed solution approach with understanding of some given sample test cases. And further, we will have a quick go through of the C++ implementation of the code. The problem statement goes as follows. We are given a rooted tree with n vertices numbered 1 through n and the root is the vertex number 1. Also, it is given that for each vertex, the parent of the vertex v is pv and pv is always less than v. So as you can see here that we have drawn the tree for the sample test case given in the question. You can see that the parent of 2 is 1 and 1 is smaller than 2. Similarly, parent of 4 is 2 and 2 is smaller than 4. So this condition will be always followed in the whole tree except for the root because root has no parent, right? Uh, Additionally, we are also given a prime number p and a set AP is defined such that it contains all integer sequences of the length n such that each element of the sequence is a number between 0 and p minus 1 inclusive. So for example, if the given prime number is let's say 3, then the sequence of length 4 can be 0, 1, 1, 2 because there are 4 numbers in this sequence, that is n is equals to 4 and the prime number was given as 3. So all the numbers in the sequence are between 0 and 2 inclusive. Okay, now moving on, there's also a definition of LCA given over here in the question, but that's just a fancy way of writing the definition. If you have the general understanding of a tree, then basically LCA is nothing but the least common ancestor. So to give a quick example, if I ask what is the LCA of 4 and 5, that is this node 4 and this node 5, we all know that the least common ancestor of both these nodes is 1, right? Similarly, the least common ancestor of 4 and 6 is 2. So I think everyone knows the basic definition of least common ancestor if you have the general understanding of a tree. So moving on, now comes the definition of the LCA convolution, which is the main crux of the question. So in the question, LCA convolution is defined as a sequence C and the operation is C is equals to A star B, where each element of C, that is Cx, is defined in the following way. But again, this is a complex way to write the definition. We are going to write the simplified version of this. So what I suggest is that if you take pen and paper and for this given sample test case, if you try to write the expression for C1, you will understand that what this given definition means in a simplified manner. So I'm going to straight away go to the result. So the result comes out to be that Cx is nothing but sum of Ai into Bj modulo P such that LCA of I comma j is equals to x. So all the pairs I comma j for whom the LCA is x, we have to multiply and sum up their values from the sequence A and B, and that is nothing but the simplified definition of C of x. So we are going to make use of this definition in our solution. So please make a note of it. And that's it. That completes the information given in the question. Now let's come to the task at hand. So the task that is given to us is that we are given this sequence C, okay, some sequence C belonging to this set AP, and our task is to find that how many sequences A exist such that C is equals to A star A, okay, where star is the convolution operation. So we have to find the count of such sequences, and we have to print any one of those sequence if it exists, okay. So definitely if no sequence exists, we have to print something like 0 minus 1, it is given in the question, or else if the count is non-zero, that is let's say some 4 sequences exist, then we have to print any one of those sequence A, and that is the task at hand. Also remember that the count can be quite large, so we have to take care that the operations have to be modulo this number so that they fit in the integer range. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. So to begin with our solution approach, we have the sample test case with us to help us understand the solution better. Of course, the case is given with the number of nodes n, the prime number p, the tree itself, and the initial array c, which is given to us. What we have to find? We have to find the number of possible sequences a and one such sequence a. So according to our simplified definition of convolution, if we try and write the expression for the leaf node, the expression would look like, for example, for node number 4, the expression would look like C4 is equals to A4 into A4 modulo P, because 4 comma 4 is the only pair for which the LCA is also 4, right? So for leaf nodes the expression is pretty simple, so we are starting with the leaf nodes. So in general, if you write the expression for any leaf node, the expression would look like Cx is equals to Ax into Ax modulo P. So this is now a math problem to solve, right? Because the expression that we are seeing right now, it can be expressed in number theory in this format as well. That is, we can write Ax square congruent Cx mod P, right? So this can be written as well. And if we try to rename these variables, so it looks like x square congruent q mod P. And in number theory, this congruence is quite famous, and in this congruence, the quantity q is known as the quadratic residue. So I will mention over here, q is called the quadratic residue modulo p. Okay, so q is the quadratic residue modulo p, and now we have to figure out a way to find a solution for x from this congruence. Okay, so moving on, in number theory again, the existence of solution for the congruence of the type x square is equals to q mod p is given by the Euler's criteria, and it states that the solution exists for this congruence if the condition q to the power p minus 1 by 2 modulo p is equals to 1. So if this condition is satisfied, then only a solution for this congruence exists. So we would be checking this condition first before finding the solution for this congruence, and if the condition is satisfied, it means that the solution exists. So now we need an algorithm to find the solution for this congruence, and here comes the Tonelli-Shanks algorithm. So let me mention the name of the algorithm. The algorithm name is Tonelli-Shanks, and this algorithm is popularly used to find the solution for the congruence of the type x square congruent q modulo p. Okay, if the solution exists. So Once we know that the solution exists, we will simply use the Tonelli-Shanks algorithm to find the solution. But what happens if the solution does not exist? That is, this condition comes out to be false. So in that case, we just have to stop our process because we know that there doesn't exist any value of x for which this congruence is true, right? So if at any step in our process, the condition comes out to be false, then we simply stop our process and print our final answer for the test case as 0 and -1. That is, there are 0 sequences of A which satisfy the condition given in the test case, and the elements of the sequence are not possible, so we just simply print -1. So this is stated in the question. So if the answer does not exist, we simply just print 0 and -1 on separate lines. But now let's see that if the answer exists, how to move forward and find the answer for all the nodes. That is, we need to find the answer for A1, A2, A3 and all the way up to AN, right? Finding the answer just for the leaf nodes isn't enough. So let's see how to find the answers for all indices. So to find the answer for any general node, our basic strategy or idea is going to be as follows. First, we will start by finding the answers for the leaf nodes. That is, we find the answer for node 4, 6 and 5. That is, now we have the answers for A4, A6 and A5. And now what we do is that we move level by level up all the way up to the root. That is, we are moving bottom up in the tree. So because now if we have to find the answer for A2, then we know that the expression for C2, as you can see over here, the expression for C2 only contains the AI values that are present in the subtree of 2. That is, I can mark over here, this is the subtree of the node 2, right? In the red color you are seeing on the left. So for finding the value of A2, the expression of C2 only contains the terms consisting of its subtree, because all I comma j are such that the LCA of I comma j is nothing but x. So that is why we are going bottom up in the tree, so that at any point the values that we require are already computed. Now, for example, if we try to write the expression for C2, you will see that on the right hand side all the terms, that is AI, AJ, are the ones present in the subtree of node 2, right? That is A2, A4, A6, all these nodes are present in the subtree of node number 2. So the expression will look something like this. I have written it beforehand because it's quite long. Now further, if we try and simplify this expression by reordering the terms, the expression would look like. And now if I try to rename the variables, so let's say if I rename the variables in the following manner, such that A2 is the term that we don't know, so I name it x. So I can write this as x square plus 2x into A4 plus A6 plus 2 A4 A6, and everything this is present modulo p because it's given in the question, right? So now you can see that this looks like a familiar quadratic, right? Because it's a simple quadratic in x, and we know that how to find the solution for x from a quadratic. So using the quadratic formula for a general quadratic, we know that x is nothing but minus b plus minus under root b square minus 4ac upon 2a, right? So if we substitute these constants from our given quadratic or from the quadratic that we have got, so it would come out to be, you're wondering what happened to this 2a, right? So the if you take out common terms, that is 4 inside the under root and 2 from this from here, it cancels out. So this is the expression that you would get finally after simplifying. This can be even further simplified because inside the under root some terms are going to cut. So for example, it will become, that's the final expression we are getting for A2. X is what? X is nothing but A2. Let me write over here. X is nothing but A2. We have just renamed the variables, right? And this expression right here, which we have in front of us, is going to help us observe the general form of expression for any node. So till now we knew that the expression was of the form Cx is equals to summation ai aj, but that was for Cx. We actually need to find the unknown term, that is Ax. So we renamed Ax as just x, and we have come to this conclusion for just the node number 2. But now we will see that this helps us actually getting the general form for any node. So on observing more carefully and writing such expressions for more number of nodes, you will observe that the general expression is nothing but uh, actually x is equals to minus the subtree sum of the node x plus minus summation of subtree sum of v squared, where v belongs to the subtree of, or actually v belongs to the uh, child of x, and here we also have a plus cx. So that is our final expression. Here, what do I mean by subtree sum? So if you go back and see the tree diagram, so this tree diagram, I'll just redraw it down. So the tree diagram was something like there was a node over here that is 2, then there was a node over here 4 and 6, right? So the subtree of 2, that is our current x, consists of 4 and 6. So you can see here that we have the subtree sum over here, and here we have the summation of the squares of the subtree nodes. So 4 is a child of 2 and 6 is also a child of 2, and we have their squares inside the under root. So this is the simplified expression that we get after some observations and writing down the expressions manually for more nodes. Like here I have just shown for A2, but you can try it for other nodes and you will get that why I am saying that this is the general expression. It's actually better if we write this as a of x, because then you would not be confused between what is this x and what is this x. So just because I had written a of 2 as x, I wrote here x, but it is actually a of x. Okay, so all this expression is for finding the value of a of x. So now if we do some let's say renaming of terms, so we can write this as a of x is equals to minus b plus minus under root d. So whatever is this quantity, I have named this as b, and whatever is inside under root, I have named it as capital D, so that it becomes easier for us to understand. So what now? So now we have the expression in terms of very simplified variables, right? And now again we are going to use the Tonelli-Shanks algorithm to find this value of Ax. How? We know that under root D has to be an integer for Ax to be an integer. So the possible solution for this term is found out using the algorithm again. And let's say that the value that it returns is named as the variable val. So now our expression is Ax is equals to minus b plus minus val. Okay, so remember that the algorithm does not guarantee the solution. It tells us whether the solution exists or not, and if it exists then it returns one such solution. So if the solution does not exist, then we have to stop the process. We have seen earlier that if the solution does not exist, we simply stop the process, break from all the loops, and just print 0 minus 1 as the final answer for our case. But if the answer exists, the answer will be stored in the variable val, and then there are again two cases over here depending on the value of d. So if the value of d was 0, it means that Ax has only one potential value, right? And what is that value? That value is nothing but ax is equals to just minus b mod p, or else if d was non-zero, that is, I'll write here else if d was not equals to 0 and solution exists, it means that some value VAL was returned by the algorithm. So there are now two potential values of A of x. So we'll just take one of them. So for example, we can write now the value of A of x is nothing but val minus b modulo p. That is one value of A of x. But remember, we also have to keep a track of the count of number of A sequences. That is, it in the beginning we had seen that we have to find the number of sequences of A such that C is equals to A star A, right? The convolution operation. And we have to find how many such A sequences are possible. So for a particular AX value, if there are two potential values, then we have to multiply it by 2. That is the count that we are keeping, that gets multiplied by 2. So in this else if case, one more thing happens, that is count gets multiplied by 2. And what is the other case? The other case, the else case, let me write it down. So the else case is that d is not equals to 0 and solution does not exist. It means that we have to just end our process and print 0 minus 1. So again, to see the summary of the three cases, if d is 0, it means that A has only one potential value, so count remains the same, that is our A count remains the same. If the solution exists and d is not equals to 0, count is multiplied by 2 because there are two potential values for that particular A of x, and we have to just save one of those values, so we take val minus b as our value. And in the else case, solution does not exist, so we break and just print 0 minus 1. So that basically sums up our solution approach, and now let's see that how to implement this in C++. Also, did you know that CodeChef also conducts free live classes on Unacademy where we teach every possible topic on competitive programming? We have beginner level courses like Introduction to Programming in C++ or Java, basic data structures, recursion, as well as advanced courses like dynamic programming, graph theory, and segment trees. These courses are conducted by top coding experts who have been ICPC World Finalists, IOI medalists, or have worked in top product companies like Facebook, Google, Amazon, LinkedIn. All you need to do is download the Unacademy app or register yourself at unacademy.com and select your goal as competitive programming. You can also take the paid plus subscription to get additional features and individual level support. In plus subscription, we have a large set of problems associated with each topic covered. Not only that, we also have 6-star and 7-star rated teaching assistants to clear all your doubts during and after the live sessions. Also, don't forget to use my referral code DarshanCool25 while subscribing to get an instant 10% discount. So to begin with the C++ code, for each test case, we start by taking the input of n and p, which is the number of nodes and the prime number p. Further, we take the input for the tree structure, that is given in the form of parent of each node. So we input the parent of ith node, and in the adjacency list of parent, we insert the node I, and that's how we create our tree. So it is represented in the form of adjacency list here. Okay, and we also have a vector C which stores the given input sequence C. So we do that as well. After that, I initialize two vectors, that is subtree sum and answer. So answer is my final vector which is going to store the values of A sequence, that is A of 1, A of 2, A of 3 for each node. And subtree sum, as the name suggests and we have discussed in the solution, subtree sum will store the sum of the values of A of I such that I is present in the subtree. Okay, so initially all the subtree sums are 0, and also I have initialized all the answer variables to also 0, and count is the total number of sequences of A possible. So we have to also output the count. So first we have to output count, and then we have to output any one sequence, that is our answer sequence. So once we have initialized this, we start with iterating in our tree in bottom up manner. That is, first we have to find the answer for the leaf nodes, and then the above level, and so on all the way up to the root. So instead of applying some traversal like DFS or BFS, observe that it was given in the question that the parent of each node always has a number smaller than the node. So if you carefully look at that property, uh, you will notice that the nodes always have numbers in the increasing order from top to bottom. So we just have to iterate them in reverse order, that is n to 1, and it will be guaranteed that every time we are calculating the answer for some v, the answer for all its subtree nodes is already calculated. So I don't do any traversal, I just write a for loop and reverse iterate from n to 1, and that handles my bottom up approach. So V is my current node. So D, that is the discriminant value which we were writing inside the square root in the solution, that consists of the value C as we have seen. So I initialize it with C of V, and then for all the children of the node V, I increment the subtree sum. The subtree sum of V should consist of all its um, children nodes subtree sums as well, and at the same time inside under root we have to add the square values of them. So there I am adding subtree sum of x squared, okay, 2d, and once we have done this, it basically completes our this formula. So now we have the subtree sum that we require, and we also have the summation of subtree sums squares for the child of v. And once we have that, we now go to the algorithm of Tonelli-Shanks, which tells us whether a solution exists or not, and we just store the answer in val. So this is the function. I have defined it above my int main, and it just returns -1 if the solution does not exist, or else it returns with a solution. So once I call this function, as discussed in the solution, if d is 0, it means that there is only one probable value of a of x, that is here answer of v. So that is just 0 minus b modulo p. So the sub function, as you can see over here, the functions like sub, add, these functions are modulo functions. So they take care that always I am doing the operations modulo p. Okay, so I just store 0 minus b modulo p in my answer. Else if val is equals to -1, it means that the answer does not exist. So I just put count is equals to 0, that is my count of possible sequences as 0, and just break out of my whole process. Or else if the answer exists, it means that d was non-zero. So I multiply my count by 2 and take the modulo as given in the question, and at the same time I store one potential value in answer of v, that is val minus b. We have discussed it over here, right? The answer is what? A of x is val minus b modulo p. So that I store over here. And after all this is done, in subtree sum of v, I also have to add the answer of v, because now I know the answer of v. So now I'll be going one step up, so I need to include my answer of v in subtree sum of v. So that I do over here. Again, that also has to be a modulo operation. So again, everywhere I'm using my modulo defined functions like add, sub, mul, and that's it. This for loop is basically my whole process, which is the bottom up process. And once we are done with this process, I check if my count is 0. If my count is 0, I simply have to output 0 and -1 as suggested in the question, or else I output the count and the a array, that is answer of I, for that is a of 1, a of 2 up to a of n. And that's it. That completes our solution. Now, without wasting any more time, let's submit this code on CodeChef ID and let's hope for a quick AC. Great. So our solution works.